the cost, not immediately.
At what point do you want?
Well, it's gonna be cool. Just like.
All right, let's get started. So we are in the viscous and compressible flow section, and we have already looked at viscous flow and the boundary layer separation, right? And this week, today and on Wednesday, we're going to be looking at transonic and supersonic flight, respectively. All right. So as you've done the lab session last Friday, if you look at the geometry, I mean, we call it the F-16 model, but this is really an airplane model that's designed to fly supersonically, right? So today we are going to look at what is really driving the kind of a design with a very, very thin wing, very thin airfoil, and highly swept wing, okay? So first of all, let's actually look at how does the aerodynamics change as we go supersonic. So these are all computed using the same software as you were using for the homework. So whatever geometry you build, you can just, if you have spare time, you can launch additional calculations at higher speeds to see how your model behaves as it goes transonic and supersonic. And in particular, you can actually observe how the transonic and the supersonic behavior would be dramatically different from what I'm showing here, which is a very conventional subsonic geometry with a straight wing, non-swept wing, and a much thicker airfoil. So I think this is using the NACA 2412. Basically the same airfoil like Cessna uses, okay? And you're gonna see how the transonic and the supersonic flight is going to dramatically change how the aerodynamics behave on this airfoil. So this is the pressure coefficient, okay, at a subsonic speed. So what we are looking at here is a Mach number, I think around the 0.75. So what you see is that the pressure coefficient is actually still quite similar to what a subsonic airfoil would look like. Although we already see there is a significant effect of Mach number already. So the x-axis is Mach number, the y-axis, the blue is the lift coefficient, and the red is the drag coefficient. Okay, we already see that the lift coefficient actually increases for the same angle of attack. And the drag coefficient also is starting to increase, but like only a little bit. Much, much less than the dramatic rise as you further increase in Mach number. All right, and just to watch carefully on the pressure on top of the wing. Okay, so still, this is a highly cambered airfoil, right? And from the thin airfoil theory, we know that even in incompressible situations, very low Mach number, we would have the highest suction, the lowest pressure, somewhere not exactly on the leading edge, but somewhere between the quarter chord and the half chord, right? That's basically what you can compute from X-foil. So this is still qualitatively very similar, although we are going to work a little bit on quantitatively how the pressure is actually different from an incompressible situation in a little bit. Now let's march on higher Mach numbers to see what actually happens. So this is at a Mach number slightly more than this point with the peak lift coefficient. So let's go back and forth to see what's changed. All right, so this is a 0.75, this is 0.8. 0.75, 0.8. What is happening? Any observations? Yes?
The low pressure area on top of the wing
it moved back a little bit, right? Again, 0.75, 0.8. That seems to be the only significant effect that's happening, right? 0.75, 0.8. Okay, so this is actually responsible for the famous Mach tuck that actually was responsible for a lot of accidents in the beginning of transonic flight, when airplanes start to be fast enough to suffer from compressibility effects. Because what is the effect of the suction region moving backward? Okay, what would the pilot feel when the peak suction moves a little bit more and more backward? Yeah? Would push the nose down, right? The center of lift shifts towards the tail, right? It would push the nose down. And as we are going to see a little bit later, if we have a horizontal tail over here, at this Mach number, the horizontal tail would also suffer from a loss of control authority. So this effect would push the nose down at the same time when the pilot is having a harder time pulling the nose up, right? So this is a big and significant effect that the center of lift is shifting backwards. And another thing that might not be that obvious, except for you watch a little bit closer to the tip of the wing, is that if you look at how the pressure transitions slowly from high pressure to low pressure here, but when the pressure transitions from low pressure back to high pressure, there seems to be a very distinct line, right? So if you go back a little bit, there is already a very distinct line inboard, but outboard you still see a fuzzy region transitioning from low to high pressure. But as you go a little bit faster, the line extends towards the tip of the wing. Actually, in both cases, there are shock waves already. Okay, so this is already a shock wave, except for it kind of disappears towards the tip. This is now an even stronger shock wave, right? That actually extends closer and closer to the tip of the wing. Okay, we're going to see that why we have shock waves even in subsonic speeds. This is still Mach 0.8, and we'll see like what is happening. Why do we have shock waves at less than Mach 1? Now going even further, so this is now about, well, I don't, this is probably Mach 0.85. And the effect is even stronger. Basically, we see a further extension of the shock wave towards the trailing edge, right? The Mach tuck effect gets even stronger, and the shock extends almost to the tip of the wing. Okay, now this is at closer to Mach 1.9-ish. The effect continues. You have now the shock wave extending almost towards the trailing edge, and actually in this situation, the suction, the flow at the top of the wing is mostly supersonic already. All right, although the flow at the free stream is still Mach 0.9. Now, this is exactly at Mach 1. All right. So what happens is that now the shock wave actually moves exactly coincidental with the trailing edge of the wing. Okay, so from probably this region to the entire trailing edge of the wing goes supersonic. And you also see some faint line on the fuselage, right? That's actually a visualization of this shock wave. I mean, you don't see the shock wave in 3 dimensions just from the pressure plot, but the impression of the shock wave on the fuselage is clearly visible from here. And that's also kind of visible if you look at before, right? If you look at over here, you already see the imprint of the shock wave on the fuselage. But as you go back here, this is actually clearly a supersonic shock wave, what we call a, instead of a normal shock, as you see here, this is now an oblique shock wave. All right. Okay, so let's actually start to. So finally, we're going to go into the supersonic range. But at this point, let's actually work out what is happening on the air. when we are marching towards Mach number zero, marching from Mach number 0 all the way to Mach number 1. Okay, so let's actually focus on this region first, right? When you have a Mach number, I'm saying greater than 0.5, but really when you're starting to have a non-zero, non-negligible compressibility effect, what is actually happening here? So what principle are we going to use? Remember, what is the definition of compressibility, right? When we are still working on a fractional sensitivity, what is the ratio of d rho over rho to du over u? Which means if I increase my speed by 1%, okay, how much does the density change? So first of all, is the relationship positive or negative? If I increase my velocity, does my density increase or decrease? Remember, like when we were standing on the wind tunnel, we had the question of when the flow goes from upstream of the work section of the into the work section, there is a contraction ratio of 8:1, right? So the speed increases, but by a factor of more than 8 or less than 8. Remember the answer to that question? More than 8, right? Why is it more than 8? Why do we have a speed increase of more than 8 when the contraction ratio is 8:1? Yes?
That's the drop.
Because density dropped, right? Okay, and the reason density dropped is because pressure dropped. So what is driving the flow to go from a low speed at the bigger cross-section to high speed at the smaller cross-section is the density gradient. It's the pressure gradient, right? The pressure was high upstream and low downstream. That's what accelerates the flow. So if pressure has decreased, density decreases, right? We are assuming the flow is isentropic. So the fractional sensitivity of a density change to pressure change is what? It's 1 over gamma, right? Where gamma is 1.4 for air. Okay, so basically as velocity increases, so this is positive, the pressure has to drop. So dP over P, right, would negatively correlate with du over u, and d rho over rho positively correlates with dP over P. So d rho over rho has to negative correlate with du over u. And the ratio we have worked out turns out to be what? Anybody remember that? Huh? Minus m squared, exactly. Right, so that's what's defining the square of the Mach number being the quantity, the quantitative measurement of how compressible the flow is. All right, so this is basically probably the most fundamental thing, right? If you remember anything about compressible flow, that's probably the thing that you can really derive almost everything relating to compressible flow by using this principle. Okay, so now today, let us actually start deriving our first consequence of compressibility. So that is, let's actually look at a incompressible flow field. So this is what's coming from the flow builder, right? The flow around a symmetric airfoil, basically by placing a bunch of vortices and sources and sinks. So this is the airfoil. Very bad drawing. So this is the airfoil. And let's work out two scenarios. One scenario is that we have a stream tube, let's say this stream tube, that decelerates all the way to the stagnation point. Okay, the question is, okay, so basically because the flow decelerates, the pressure has to increase, right? Because that's what's driving the deceleration. So the question is, as you are decelerating, in the incompressible flow field, the deceleration has exactly the effect of the area times velocity being a constant. So as you're decelerating, my stream tube increases while the velocity decreases. Okay, so if you know the geometry of the flow, then you would know exactly how much the velocity has decreased, and from how much the velocity has decreased, you would know how much the pressure has increased. Now let's work this out in a compressible flow. So let's work out in two scenarios. One scenario is scenario 1 is Mach equal to 0. Let's just say Mach square equal to 0. Scenario 2, just use a red for scenario 2, is Mach squared equal to, let's make it a little bit more, well, let's make it less significant. So Mach squared is equal to 0.5. All right. So here the Mach number is about 0.7 something, right? So already a very significant compressibility effect. So in both cases, let's assume the geometry of the flow is the same. So basically the area, a very small stream tube. Okay, so let's imagine the area is equal to a unit of 1 in the free stream that has increased to 1.1 and then 1. So basically, let's imagine the area has increased by 10% and then another 10%. So another. Okay, so let's work out how much the velocity has changed on these two subsequent area expansions, and also how much the pressure has increased. So how much the velocity has decreased and how much the pressure has increased. Basically, let's approximate the 10% increase as if they are infinitesimal, right? And they use fractional sensitivities like that to work that out. All right. So in both scenarios, the first question is how much velocity decreased, and the second question is how much the pressure increased. And if you work that out, then a subsequent question is the following. Consider a different streamline, so streamline number 2, that instead of increasing in the width, the streamline number 2 actually is above the airfoil. It actually decreases in width, just like this one, right? So it's a decrease of 10%, and then another 10%. Again, let's work out how much the velocity in this case has increased and how much the pressure has decreased in this case. So basically, really what I'm asking is 8 questions, right? Because 2 scenarios, okay, and 2 different Mach numbers, and the 2 different stream tubes, one expanding, one shrinking. And for each Mach number, each stream tube, I'm asking 2 questions. How much velocity has changed and how much pressure has changed. And use fractional sensitivities like this. And of course, you have other fractional sensitivity equations, right? You have, for example, U times the area times the density is equal to a constant because of conservation of what? Mass, right? So that's true for every streamline. and you can derive all kinds of fractional sensitivities from there, right? So basically, use the principle of conservation of mass and the conservation of energy, right, as well as this compressibility effect to answer these 8 questions. See if you can work out the most significant effect of compressibility yourself. All right, let's get started. Hey, we get talks over All right, I think most people are done or have at least are getting towards your conclusion, right? So can we conclude some intuitions or results, some things you can generalize from this analysis? First of all, when we are looking at velocity increase or decrease, does incompressible case or compressible case has a stronger response of velocity with respect to a change in the stream tube area? Compressible, right? So in a compressible flow, the velocity would respond a lot more strongly to the geometry of the flow. Okay, this explains to a large extent why for the same geometry, the same angle of attack, the lift coefficient actually would increase as you increase the Mach number. Why? Because the geometry of the airfoil did not change, right? The geometry of the flow tubes, of the stream tubes, well, it changes a little bit, but qualitatively it won't change. It still shrinks at the minimum pressure, right, and expands as you go downstream of the minimum pressure point. So the geometry did not change much, but the velocity at the minimum pressure point proportionally changes by a lot. So for example, if I have an incompressible flow, and this is a stream tube of incompressible flow, the geometry shrinks, the stream tube shrinks by a factor of 2 at the lowest pressure point compared to the free stream, right? We know that if it's an incompressible flow, then the velocity would be equal to twice V infinity. But if we have a compressible flow, the velocity here would be probably a lot more than twice V infinity, right? Okay, and in particular, if I do have a Mach number square equal to 0.5, which means my Mach number is equal to 0.7 something, the velocity here would be, well, probably supersonic, right? Greater than Mach 1. This is why we would have supersonic flows, even if the Mach number is actually, could potentially be a lot lower than Mach 1 when we start to observe supersonic flows on top of the airfoil. Okay. Another thing, when you look at the pressure, is the pressure increase or decrease is actually also more aggressive. So when I ask you to work on the pressure, you worked out the dP over P, right? And I should have asked what is the pressure coefficient. So instead of a dP over P, if you work out dP over half of rho u squared, that's the pressure coefficient. You're going to see the pressure coefficient for the compressible flow case would also respond more aggressively compared to the incompressible flow case. In particular, that means in the stagnation stream tube, when the velocity goes to 0, you're going to see a pressure coefficient greater than 1, okay, at the stagnation point. So for incompressible flow, that never happens. For incompressible flow, the pressure at the stagnation point, by definition, is equal to 1, right? Because pressure coefficient is defined as the pressure divided by half of rho u squared. And for incompressible flow, we have the incompressible flow Bernoulli. So basically, stagnation pressure has to equal to 1. But for compressible flow, the pressure coefficient is actually going to be greater than 1 at the stagnation point. And also, the pressure coefficient on top of the airfoil would actually be more negative than if you have an incompressible flow. Now, let's actually take the argument to its extreme point. Think about what happens when Mach number is equal to 1, right? I think all of you has worked out the formula that a dA over A is equal to minus of 1 minus the Mach number squared times du over u, right? I think that's for example, when Mach squared is equal to half, that means I have a 0.5 here, right? And du over u would be twice as much as in the incompressible flow case. But maybe you've thought about this. But in the accelerating stream tube, m squared is no longer a constant, right? For the decelerating stream tube, m squared is also not a constant. But as I'm decelerating, m squared decreases, right? So the compressibility effect would become less and less significant as I approach the stagnation point. But on the accelerating stream tube, it's the opposite. As I accelerate, m squared keeps increasing. And the compressibility effect keeps increasing. And my du over u would be a lot more, right? So I mean, another way to write this is du over u is equal to 1 over minus 1 over m squared of dA over A. So for the same dA over A, as I accelerate, as dA over A is negative, du over u is positive. As I accelerate, m squared also increases towards 1. And this negative thing just becomes more and more and more negative until at a point when Mach number actually gets to 1, what happens? Well, when Mach number actually goes to 1, this is what we call like a singularity point. So it's a singularity in the sense that if I have still a non-zero dA over A, du over u has to be infinity. It cannot happen, right? So this is what we call the flow choked. It is choked, meaning that the stream tube area cannot decrease anymore. Okay, so just imagine a case where m squared is equal to 1. It's easier to look at in this case. Look at this formula. So this is equal to a 1. Okay. dA over A has to be exactly 0, right, when Mach squared is equal to 1. Now imagine a little bit downstream and a little bit upstream. of the Mach equal to 1 point. What is happening? So a little bit upstream, we still have subsonic flow, right? So we still have 1 over m squared being negative. When 1 over m squared is negative, the flow is accelerating, right? So du over u is positive, which means dA over A is negative. Upstream of the choking point, the stream tube area is decreasing. Now consider the downstream. Two possible scenarios. One possible scenario is the flow now gets to a maximum speed of Mach 1, then decreases back to subsonic speed. In that case, du over u would be negative, right? 1 over m squared is also positive because the flow decelerates back to subsonic. So minus 1 over m squared times du over u is positive or negative. The whole thing, yes, is going to be positive. That means dA over A is positive. Downstream, the flow expands. Okay, so that's when the flow reaches Mach 1, then decelerates back. But how about the other case, when the flow further accelerates to supersonic speed? That means downstream du over u is still positive. But 1 over m squared is now negative. So how about the entire right-hand side? Still positive, right? No matter what. No matter what. No matter if the flow reaches Mach 1 and decelerates or reaches Mach 1 and further accelerates. dA over A downstream of the choking point has to be positive. The area has to increase. In other words, the location of the Mach 1 flow point has to be the minimum flow tube area. Right? That's probably the most important information you can gather intuitively by just looking at a transonic flow streamlines. So, for example, if this is indeed a transonic flow streamline, by transonic I mean part of the flow is supersonic, part of the flow is subsonic. I can read where the Mach number is exactly equal to 1. How do I read it? Exactly, just look at where each stream tube reaches its minimum area, right? Here, it reaches minimum area, then this would be the Mach 1 point. And no matter if the flow further accelerates to higher Mach number or it decelerates, I know this is going to be Mach 1. Okay, now further, what happens as Mach number exceeds 1, right? As we have analyzed, when Mach number exceeds 1, further increasing area now means an increasing velocity, right? This whole negative 1 minus m squared is now positive, right? So increasing u means increasing area. If you look at an actual transonic flow case, right? So this is a actually let me show you a real transonic flow case. So this is a zoomed in view of the calculation we showed earlier. And what's the difference is that we have a cut plane. So basically this is a plane cut through a section of the wing on which we are showing you the Mach number distribution. So 1 is, just to look at the color, 1 is somewhere along this line. All right. Basically, in this entire region, the flow is supersonic. What is happening is that as the flow goes supersonic, if you look at the contours of the Mach number, right, it keeps increasing velocity. That means the stream tube area, as I move from here to here, actually would increase, right? So unlike a subsonic flow case, where the pressure, where the suction peaks here and the velocity also peaks here, right? The streamline contracts and expands. In the supersonic flows, the streamline are the same qualitatively. It also shrinks and expands, but the velocity in the expanding portion behaves completely differently. Instead of the velocity reaches a peak at the minimum stream tube, the velocity would keep increasing and the pressure would keep decreasing after the stream tube reaches the minimum area. Okay, that's what's responsible for moving the center of lift backwards as we reach and exceeds the threshold of the first point being supersonic. Okay, so that's what's happening to the Mach tuck. Now, let's start looking at the most significant feature, new feature in transonic flight. That's the shock wave over here. That's the shock wave over here. There is no natural way for the flow to transition from a supersonic condition back to a subsonic condition, right? Because the supersonic region cannot last forever. The flow downstream has to become subsonic again. But in order for the flow to slowly go from supersonic back to subsonic, you need something that doesn't occur in this geometry. You need the stream tube to shrink again, right? I mean, in supersonic flows, you need to, if you want to decelerate, you need to shrink the stream tubes, okay? And if you really want the flow to go back to subsonic again in a smooth way, you have to design the wing. I mean, that's actually what happens to a lot of the supercritical airfoils designed for transonic flight. You have to design the geometry in a way to let the stream tubes shrink a little bit and then expand further. But for this particular airfoil, it doesn't allow that. The streamlines would keep expanding because the section of the airfoil, and there is a camber over here, and the thickness keeps shrinking, right? So the stream tubes keep expanding. The flow has to transition to a subsonic flow in a very abrupt way. That's what the shock wave is doing. So basically, the flow, instead of decelerating isotopically, which has to follow the formula we derived, all right, it decelerates anisotropically. So there is a very thin layer. In the thin layer, a lot of viscous effect happens that basically decelerates the air in a way that's totally different from our derivation. Okay, so that's what's in the shock wave. And in the shock wave, energy is, so of course, mass is still conserved. Okay, momentum is still conserved. Energy is conserved, but there is a lot of mechanical energy transferring to thermal energy. Okay, so if you look at the wake of a transonic aircraft, you can actually spot the area of the air that has passed through a shock wave by a heat signature. Right? So basically, if a streamline passes not through a shock wave and gets into the wake, you may have kinetic energy here, but the temperature wouldn't increase. But if a stream tube passes the shock wave, you're going to see that actually the flow, even after the airplane, long after the airplane passes by, it both has kinetic energy and have additional thermal energy. Well, that of course means additional drag for the airplane, right? Because the airplane has to supply that thermal and kinetic energy in the wake somehow. So that's a new type of drag we call wave drag. So what is wave drag? Wave drag is basically the drag due to an increase in energy in the wake, right, as the air passes through a shock wave. All right, any questions so far? Nope. Okay. So this actually is it's some flow visualization of the shock waves on airfoils. Oh, and sorry, one additional thing I forgot to mention in the calculation. Look at here. So this is the Mach number contour, right? Look at the dark blue region over here. That's very low speed, right? Anybody wants to guess what's happening here? Think about what we studied last week. It is turbulent flow, but why? Separation, right? Why would the flow separate exactly here? Adverse pressure gradient, exactly. So over the shock wave, then what's happening is that we do have conservation of momentum, right? The flow suddenly decelerates from supersonic speed back to subsonic speed. That means the pressure has to what? Increase suddenly over a very short spatial distance, right? The pressure increases in such short distance that whatever viscous force in the boundary layer doesn't have enough time to prevent flow separation. So whenever you have a strong shock, by strong shock I mean the pressure increases by a lot, the flow is probably going to separate. All right, and this separated region, think about what the low Mach number means in the frame of reference of the ground, right? A low Mach number means the velocity relative to the airplane is small. And if you look at the wake, that means the velocity relative to the ground is actually fast. It goes with the airplane, right? Additional kinetic energy in the separation region. That's basically, flow separation drag. So this shock, this wave drag and the drag due to flow separation is really responsible for the very dramatic rise in the drag coefficient as the flow goes into transonic regime. And actually, if you look at this, if you look at this stupendous rise in the drag coefficient, right? It actually starts to drop as the Mach number exceeds 1. So as the Mach number exceeds 1, at least you don't have the flow separation drag, because remember you can also spot from the streamlines, right? The flow basically goes in the opposite direction after it passes the shock. So remember, like as the flow further as the airplane further accelerates, the shock is moving more and more downstream, so the flow separation region actually decreases. And at Mach 1, the whole flow separation region disappears, right? You no longer have much separation drag, but like the wave drag gets more and more because the flow reaches even more supersonic speed before it transitions back into subsonic speed, and the shock gets stronger. Yes?
Can you explain why we have that strand of the blue strand of low Mach number in the middle?
Oh, sorry. On the surface of the wing, we are showing pressure. Like we have two different visualizations. One is on the surface of the geometry, we are showing pressure. And on this cut plane that cuts through the wing, we are showing the Mach number. Sorry, it doesn't make sense to show the Mach number on the surface of the airplane because Mach number is equal to 0, right? It's wall. It's a solid wall. I mean, this is a viscous calculation. All right. Right. Sorry, I didn't explain that very clearly. Okay. Yeah. So this is a visualization, and you can very clearly see the flow separation and the shock wave sitting over here. Okay. So let's actually, I don't know if I have time today to explain what happens across a shock, but let's get a very fast intuition about what happens. Okay, so across a shock wave, m greater than 1, m less than 1. That's the basically the speed suddenly decreases. Okay, now the most informative analysis around the shockwave is to draw in a control volume like that. A control volume that's very thin just encompasses the shockwave. So what's happening across the shockwave? So first of all, conservation of mass, right? So rho times u times area, which is the same across the shockwave, right? So by drawing a very thin control volume, the area barely changed. So the area is the same on the left and on the right. So rho left, u left, has to equal to rho right, u right. That's conservation of mass, right? We are taking advantage of the control volume being very thin and the area is the same. So the fact that the velocity decreases suddenly by a lot means the density actually would increase suddenly by a lot, right? Just from this. Because UL is a lot faster than UR. Rho L, let me just make sure this is different from P. Rho L is going to be a lot smaller than rho R. Now conservation of momentum. What is the momentum flux? The momentum flux is rho L UL squared, right? And then I need to add the pressure on top of this. And that has to equal to the rho R UR squared plus PR. All right. Now, the analysis is interesting because I can write this rho L UL squared as a rho L UL times another UL. And I can write the rho R UR squared as rho R UR times another UR. And this parenthesis, just by this conservation of mass, is equal to that parenthesis, right? Okay? That means that as UL is faster than UR, so rho L UL times UL again has to be less than rho R UR times UR, right? Just because of the parenthesis is exactly the same. And we know that UL is greater than UR. That means PL and PR, which one has to be larger? PR, right? So basically conservation of momentum tells you that a sudden decrease in velocity has to lead to a sudden jump in pressure. And finally, these are all qualitative analysis. And if you want to know exactly how much the pressure has jumped, how much velocity decreased, how much density has jumped, you also have to write down the conservation of energy. And that's probably too complicated for today. Basically, if you write down all the three equations and solve, you're going to generate numerically what we know as the shock tabular, right? So basically, you can look up the numerically computed tabular and figure out exactly how much velocity decreased, pressure has jumped, etc. So we'll start from here on Wednesday's lecture. So this is the numerical solution. All right.